Okay, so let's begin to dig into section 11.8 and see what lay ahead. All right, it is entitled Correlation and Regression Analysis. When we get done with this section, we will understand how to interpret a scatter plot, and we'll look at how scatter plots are constructed for ordered paired data. We're also going to calculate a very useful statistic called the correlation coefficient for an ordered pair data set. And again, gives us a numerical measure as the strength of relationship that exists between the X and the Y data. All right, and we're also going to take an ordered pair data set, and we're going to be able to come up with an equation that models the data, a linear equation that models the data the best. And for that reason, the line we're about to find for this data is sometimes referred to as the best fit line, or sometimes it's called the least squares regression line. Okay, or we just call it the regression line. Once we find that linear equation that models our order pair data, we can use it to make predictions. Okay, so what is correlation? Basically, correlation is the existence of a relationship or lack thereof between X and Y data. Okay. So if we go out in the real world and collect an ordered paired data set, we can look at the correlation between this data to see if there is a strong relationship between the data or a weak relationship. And if there is a relationship, whether it's a direct or inverse variation or relationship. When we collect ordered paired data, of course, we have our X data, which is usually called the independent variable, and the Y variable is referred to as the dependent variable. So we're collecting ordered paired data. Right? When we have a set of ordered pairs, we can, of course, plot them in the XY plane, and this plot is called a scatter plot. And by looking at the scatter plot, we can determine what type of relationship exists between X and Y, and how strong of a relationship exists between X and Y. All right, here's an example. Suppose a medical researcher selects a sample of small hospitals in the state and hopes to discover if there is a relationship between the number of beds and the number of personnel employed by the hospital. Do you think, ladies and gentlemen, that there would be a relationship between these two data values? The number of beds in the hospital, do you think it's related in any way to the number of personnel that's employed by the hospital? Do you think there'd be any relationship between those two things?
Yes.
Yes.
Okay. You know, I mean, it kind of seems like there might be. I mean, the larger the hospital, the more employees it has, and it just seems like they'd probably, you know, be able to accommodate more patients. So it seems like there would be, a relationship, and it seems like it might be a direct relationship in a sense. Well, we can investigate that when we collect data. So what we're going to do is we're going to go out and collect ordered paired data from several hospitals. The X variable represents the number of beds that the hospital offers, and Y represents the number of employees that the particular health facility has on board. Okay, so we have ordered pairs here. In fact, how many do we have? Looks like we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ordered pairs from 10 different hospitals. And what we will do is we will take these ordered pairs and we'll plot them in the XY plane, and then take a look at the plot called the scatter plot to see if there's any discernible relationship that exists between X and Y. So part A says that, yeah, just as we suspected, there probably should be a relationship between the number of beds a hospital has versus the number of employees. It seems like that would be a direct relationship. Okay. All right, so now we're going to build a scatter plot for this ordered paired data, and you just have to make sure that your X and Y axis scales are relevant for the data you collected. In other words, notice our X data ranges from like what, 28 to like 95. So you want to make sure that you have a scale laid out on your x-axis that's going to be able to show these ordered pairs. In other words, you wouldn't want a scale on the x-axis that ranges from like 100 to 500. You're not going to see any of these ordered pairs plotted. Okay, so maybe you want a scale that goes from maybe 20 to 100. That seems like a good scale. Notice the Y data ranges from a minimum value of 72 to a maximum value of 366. Because of that, you need to make sure that you lay out a scale on the y-axis that will accommodate that range. Let's see what your author did here for the scale. Yeah, it looks like your author ran the x-axis from 0 to 100, spacing the tick marks 10 units apart. And the x variable, of course, represents the number of beds that the hospital offers. The y-axis is they decided to put a scale from 0 to 400, spacing the tick marks 50 units apart, which represents the number of employees in the hospital. You can see after plotting those 10 ordered pairs that we collected from the different hospitals, you can see the scatter plot that it gives us. And ladies and gentlemen, it kind of looks like our hunch was correct. It kind of looks like as the number of beds the hospital can offer increases, it kind of looks like the number of employees the hospital has on board tends to also increase. It seems like the data is kind of rising from lower left to upper right. So that kind of like confirms our suspicion that there appears to be maybe a direct relationship, or we should say more correctly, a direct correlation between X and Y. Okay. Now, is it a strong direct correlation? How can we tell? Well, it's a strong correlation if all these points lie on a line. It does not appear that all these points lie on a straight line. And because of that, I mean, there is a direct correlation between the number of beds versus a number of employees, but it doesn't look like it's, extremely strong, because these points don't always, these points don't all hug very closely to a line or lie on a line. Okay. They're kind of like a little dispersed here a little bit. All right. So yeah, there is a direct correlation between X and Y, but it does not appear to be very strong. Well, how strong is it? We would like to become more mathematically precise in indicating exactly the strength of the correlation that exists between X and Y. And to do that, we will be developing a useful statistic called the correlation coefficient. They call it the Pearson correlation coefficient in statistics in honor of Carl Pearson, who was a prominent statistician who came up with this many years ago. Okay, so let's take a look at this here. Okay, and again, there appears to be a direct correlation between X and Y, although it's not a very strong direct correlation. One does exist. All right, so ladies and gentlemen, if we go out into the real world and collect an ordered pair data set and then come back in and construct a scatter plot, okay, how can we interpret what the scatter plot's telling us about the X and Y data here? Well, for one thing, if your points tend to rise from lower left to upper right in the first quadrant of the XY plane, we say that we have a positive linear correlation between X and Y. Or another way of saying that is to say we have a positive direct correlation or direct relationship that exists between X and Y here. Okay, and the closer all these points are to lying on a single straight line, the stronger that relationship is. You can see with this bivariate data set, this ordered pair data set, that these points tend to hug a line rather closely. I mean, if you were to put a line, right through these points here, you can see that most of the points are very close to that line. For that reason, we would say that there is a rather strong direct correlation between X and Y here. All right. On the other hand, if your ordered pair data set gives us this scatter plot signature, in this case, we would say that there appears to be a negative linear relationship or negative correlation between X and Y. Or, liaison, we would say that we have an inverse correlation between X and Y. All right. In the sense that as X increases, it looks like the Y coordinates of these points are decreasing. And if we were to kind of fit a line to these ordered pair points, a line that basically minimizes the sum of the squared distances between the point and the line, this is called a regression line. And we're going to show you how to find the equation of that best fit line or regression line that fits this ordered pair data the best. You can see that this line would have a negative slope because it's a falling line. Okay, and that's why we say we have a negative linear relationship that exists between X and Y, or we have a strong inverse correlation between X and Y. All right, any questions so far here? So the graph above here was a strong direct correlation because as X increases, notice the Y coordinate also increases and vice versa. This is a strong direct correlation. And a line fit to this data would have a positive slope since this is a rising line, correct? That's a positive sloped line. We'll show you how to find the equation of that line. It's called a linear regression line, which is the best fit line that fits your data points the best. And that's guaranteed by differential calculus too. So we got a very prestigious branch of mathematics going to bat for us and finding that equation, that linear line. And we'll show you how to do that. Suppose, ladies and gentlemen, we collect an ordered pair data set and make a scatter plot, and the scatter plot looks like this. Now, does it look like this is a linear relationship between X and Y? Doesn't look like it at all. I mean, if you were to put a line through these points here, you know, the line will hug some of the data points very closely, but it does a very lousy job for all the other data points in the data set. Okay, no matter what kind of line you try to put through here, the line will hug a couple of data points very closely, but will in general do a lousy job for the majority of the data points. This is not a linear relationship. In fact, this data set exhibits a nonlinear relationship. And to be even more precise, it looks like, ladies and gentlemen, we could fit like a parabola to this data set as opposed to a line. And parabolas are graphs of what are called quadratic functions in mathematics, second degree functions. Okay, so this is definitely not a linear relationship between X and Y. So you definitely would not want to try to fit a line to this data. You would want to rather fit a parabola to this data. In other words, you would not want to do linear regression with this data. You would want to do what's called quadratic regression and fitting a parabola to this data as opposed to a line. All right. Suppose we collect an ordered pair data set and the scatter plot gives us this signature. In general here, ladies and gentlemen, because all these points are just randomly plotted and scattered all over the place, we would say that a very weak or no linear relationship exists between X and Y whatsoever. We would say there's a very weak or literally a non-existent correlation between X and Y for such a scatter plot as this. Kind of makes sense because no matter what kind of line you try to fit through this data, it's going to hug some of the data points very closely, but in general, it's going to do a lousy job in the sense that all the other or the majority of the data points are far away from that line. Even if you try to fit a parabola to this data, you know, it'll hug some of the data points closely, like right in here, okay, but it's going to do a lousy job at hugging the majority of the points here. So quadratic regression is not even the answer here. In fact, there really is no regression or curve you could fit to this data to basically have a very good fit whatsoever, because the correlation between X and Y is very weak here, if it even exists at all. All right, now let's get more serious about this correlation between the X and Y data. In fact, we're going to become more mathematical about it. Ladies and gentlemen, the correlation coefficient that exists between an X and Y ordered pair data set is a number that describes how close to a linear relationship there is between the X and the Y data. And this statistic is represented by the letter R. So they use the lowercase letter r to represent the correlation coefficient in statistics, okay? Now, it's very important to note that the correlation coefficient always ranges from -1 to +1, where if R is equal to -1, we have a perfect negative linear relationship between X and Y, or we have a perfect inverse correlation between X and Y. Or if R is equal to +1, we have a perfect positive linear relationship that exists between X and Y, or we have a perfect direct correlation between X and Y. So again, R ranges from 1 to -1, and it could actually be equal to -1 or 1. In other words, you're never going to compute the correlation coefficient, and it's never going to be equal to like 2. Or the correlation coefficient will never be equal to like -3. Impossible. Correlation coefficient is always a decimal or a fraction that ranges between -1 and 1 inclusive. The closer your correlation coefficient is to 0, okay, is a strong indication that there is no correlation between X and Y, or you have a very weak relationship between X and Y. Any questions about this here? All right, how do we compute this correlation coefficient R? Well, we're going to show you, I promise you. So again, ladies, just to recap what we've learned so far, this would be a strong what? Positive correlation between X and Y, a strong negative correlation between X and Y. This is not a linear relationship at all between X and Y. This is more like a quadratic relationship between X and Y, and this would be no relationship whatsoever between X and Y. Okay. So we would expect the correlation coefficient for the first diagram to be very close to what number? Very close to what about? Because we have a strong direct correlation. We would expect R to be very close to positive 1. Yeah. And for the second diagram, the second scatter plot, we would expect R, the correlation coefficient, to be very close to
-1.
And for this third scatter plot, we would expect R, being a linear correlation coefficient, to be approximately about what? Very close to 0, because there is no linear relationship with this ordered pair data here. Now, if you were doing quadratic regression and you were trying to fit a parabola to this data, then we would say the correlation coefficient would be very close to +1 in that situation. But if you're trying to fit a line to this data, then the correlation coefficient indicating how well the line fits the data would be very close to 0. And for this scatter plot here, we would expect the correlation coefficient also to be very close to 0, in the sense that there is essentially no linear correlation between X and Y whatsoever. Okay. Any questions about that there? So a scatter plot gives us a very quick snapshot idea as to what type of relationship we have between X and Y, and also the strength of that relationship if we're investigating a linear relationship. Or the scatter plot can show us that the XY data has some sort of other relationship, maybe non-linear relationship that exists. All right, ladies and gentlemen, you're going to freak out, but this is the formula that is used to compute the correlation coefficient. And it does look, rather intimidating, to say the least. Notice in the denominator, we do have a square root here. And this square root goes all the way over here. So all of this is underneath the square root, all of that. And this is your numerator here. N is the number of ordered paired data, the ordered pairs that we collected in the field. Sigma sub x, this means the sum of the x values. This is the sum of all the y coordinates of all their ordered pairs. This is the sum of all the products between the x and the y coordinates of our ordered pairs. This is the sum of all the x coordinates squared. And this is the sum of all the y coordinates squared. You have to compute all these sums and then substitute them in the proper place into this formula in order to crank out the correlation coefficient R that exists between the X and the Y data. So that is the formula. You might want to jot that down maybe on your notebook right now, quickly, that formula, because we will be using it to do a couple of problems in computing the correlation coefficient of an ordered paired data set. Now, the key is, ladies and gentlemen, you got to keep in mind that all of this in the denominator is underneath the square root. None of it is outside the square root. It's all part of the radicand of the square root, what's underneath the square root. Okay. All right, so we will be revisiting that formula there in computing the correlation coefficient. And let's see, do I got my calculator? I'm going to see if I can, on my phone, I'm going to take a picture of that formula because I'll need it myself. I do not have this memorized, and you can see probably why that is the case, as this formula is not, extremely easy to remember. For that reason, you want to make sure that you have it written down in your notebook, along with maybe an example before you try to attempt a problem on Alex. Okay, so I'm going to take a picture of this formula here. Now I got it on my phone, and then I'll be able to use that for problems. All right, we all ready with this? Kind of got that jotted down there, that formula.
No.
Just another second.
Write it down. Just remember, this whole denominator is underneath this square root. So make sure you extend this square root bar all the way over. Okay. Because it doesn't look like with the PowerPoint that they've done that. So it's very important to note that, or else you won't compute R correctly. So there's a lot of summations of different things that go into this formula here. And I indicated to you that statistician Carl Pearson came up with this formula. And for that reason, this coefficient is oftentimes called the Pearson correlation coefficient of an ordered paired data set. And Pearson is spelled P-E-A-R-S-O-N. Carl Pearson. You can look him up. He made a lot of contributions to the field of statistics. All right, ladies and gentlemen, let me know when we're ready to go on here. You got that jotted down? Notice all this is enclosed in a set of brackets too. This right here, this quantity in brackets, and then this quantity is inside brackets. And we will literally have to multiply them together. There should be multiplication in between the brackets. Understood. Okay. All right, let me know when you got that. Ready to move on.
I got it.
Okay. And it's on the PowerPoint. So, if you forget it or lose it, you'll have access to that. But yeah, it probably is nice to have this handy when you could sit down and start working with Alex. Right, very important to have that. Okay, let's see if we can employ that formula, ladies and gentlemen. Let's put it to work. Okay, let's try to find the correlation coefficient of this ordered paired data set. In fact, this is the same data set, which was the number of beds in a hospital versus the number of employees the hospital had. Remember, we remarked about the correlation of this ordered paired data set by looking at looking at a scatter plot. We indicated that it appeared to have a direct correlation or a positive correlation. However, it did not appear to be an extremely strong direct correlation, as the points did not appear to lie on a straight line. So we would expect R to be positive, don't get me wrong, but we would not expect it to be, like 1, exactly 1. In order to be exactly 1, your points have to lie precisely on a rising line. For R to be exactly -1, your points have to lie precisely on a falling line. If any of the points are offset from a line, then you do not have a perfect 1 or -1 signature for R. All right, so how would we figure the correlation coefficient? Well, ladies and gentlemen, in order to do that, we need to make a table to help us compute intermediate results that we need for the formula for R. Okay, and here is the table that's going to help us take care of this. So we got our X column, we have our Y column. Notice that's your raw ordered paired data we collected in the field. All right, you got your X coordinates of your ordered pairs we collected and your Y coordinates. Make sure you keep them together. That's critical. If you don't keep these X and Y coordinates together, then all your efforts are in vain. You're going to have worthless results here. So just make sure, you know, for this ordered paired data set, you keep your X coordinate paired with your Y coordinate. Very important. All right, notice the third column is X times Y. So how did they get this 2016? Anybody? How did they get this value here?
They multiplied 28 and 72.
They multiplied X, which is 28, times Y, which is 72, and that gives you 2016. All right. And how do you think they got X squared here? How did they get to 784, do you think?
Oh, my mic been on this whole time. X times 2. X
Well, not
times
X, yeah, not X times 2, but they took the X value and what, squared it, correct?
squared, yeah, times 12.
Not by 28 by itself, 28. Yeah, 28 squared, 28 times 28 is 784. 56 times 56 is 3,136, et cetera, et cetera, et cetera. And of course, now they have a Y squared column here. How did they get this 5,184? They squared 72. Do you agree? So if you take 72 and square it, that's saying the same thing as 72 times 72. And that's how they got that big old number, that 5,184 there. And they did that for all the other values too. Okay. Notice at the bottom of each column, they then did what? What did they do at the bottom of each column? What does this sigma notation indicate they did?
They added that column together.
They added the column up, exactly. So the sum of all your X values is 572. If you added all your Y coordinate values up, you get 1,750. You added up all your X, Y product values, you would get 113,865, et cetera, et cetera. So these are the sums of each of the columns at the bottom. And we need those sums, ladies and gentlemen, because we need them for our formula to compute the correlation coefficient R for this ordered pair data set. So that's why we need to do this table, so that we can generate all of these sums that we need for the formula. So with, you know, that I strongly recommend you do build this table to help you out. Otherwise, yeah, it's going to be a real mess. This helps you to really organize your information big time here. All right. And, you know, it does take time. Don't get me wrong. It takes time to go through and form all these columns and sum them all up. For that reason, you know, I'll make sure that if I give you a problem like this, I'll keep the number of ordered pairs down to a minimum. Could you imagine building a table like this if you had like 100,000 ordered pairs? Could you imagine the amount of time that would take? Your only hope there would be using a computer system. Okay. All right. A computer could build this table within within about 1/1,000,000th of 1 second. A computer could do the whole table. Boom. Whole thing done. We cannot compare when it comes to the speed of a computer. All right, here we go, ladies and gentlemen. Now we're going to feed or substitute things into the correlation coefficient formula R where they belong. So what is n? What does this n represent again? Lowercase n?
The number of data pairs.
Yeah, the number of ordered pairs, which we had 10 of them, correct? There's 10 ordered pairs that we collected in the field. And so n takes on the value of 10 in this formula. Notice they put the 10 right here. That's for this n. And then they put 10 right here because you also have n appearing down here in your denominator. And also here too. Notice you have n here too. So you got 10 here too. And so they also substituted in all the other values where they belong. So do we understand, ladies and gentlemen, where all these numbers are coming from? How they substituted in all the values. Oh, I want to point something out very important here. This is a common mistake. A lot of students think that these are saying the same thing here. Are these saying the same thing? Are these equal to each other?
Yeah.
All right. You fell into a common trap. It's easy to, think that that should be the case. But ladies and gentlemen, this is a night and day difference. These are not equivalent to each other. Here's why. The summation on the left first had us squaring all the x values. Do you agree? And then summing them up. On the right side, the summation first of all had us adding all the x values together first, and then just squaring that sum. Let's go back and convince ourselves that these are not equivalent to each other. Let's go back to our table here. So what would be the sum of the x squared values? Do you agree it's this 37,802? That's the sum of the x squared values. Now, ladies and gentlemen, let's look at this. What's the sum of my x values? What was the sum of my x values? Oh, that was 572. So what if I take the 572 and square it? Will I get 37,802? Go ahead on your calculator and take 572 and square it. Do you get that 37,802? I think you will agree that you don't get that. Agree? You don't get that. So please don't fall into the trap of thinking that these are the same. They're totally different. Totally different things going on here. Here we're first of all summing up x and then just squaring that sum. But here we're first squaring all the x values and then summing all those squared values up. Totally different operation. All right, so I just wanted to draw your attention to that. That's a common mistake. All right, so therefore, in for the sum of the x squared values, they put that 37,802. And in for the square of the sum of the x values, they put the square of 572 down here. And notice the sum of the y squared values is not the same as the square of the sum of the y values. They're different numbers. They're not the same. All right, I want you all, ladies, I'm going to get on your calculator, whatever machine you got, and I want to see if you can dial this up. Can you get this 0.748? Now, word of warning. So you don't get a logical error, here's what you need to do. I strongly recommend that you enclose your entire numerator inside parentheses. You need to do that. Enclose your entire numerator inside set of parentheses before you hit divided by, and then your big old square root. All right. Now in the denominator, careful here. You got to use parentheses here and here. Type all this inside the parentheses times, and then you got to have another set of parentheses here and here, and all this needs to be underneath your square root. So I'm going to give you a minute or so, ladies. I'm going to get on your calculator and see if you can dial this up. I have a TI, let's see. I got like a TI 34, which is very similar to a TI 30, which is recommended by the department. But you don't really need a TI 30. You can use basically any scientific calculator to take care of business here. But my concern is, can we all do this on our calculator out there and get to 0.748? That's what I'm concerned about. So ladies and gentlemen, if you got a scientific calculator, dig it out. And let's see if you can generate this 0.748, which would be the correlation coefficient for the X and Y data for this ordered period data set. All right. So let's see if we can do that. And I do have a calculator. It's not, I can't project it on my screen, but I can use my overhead doc cam to show you how I'm typing it in on my TI 34. But I'm going to give you a moment to see if you can maybe do this. Do you even know where your parentheses keys are on your calculator? Do we even know where those are? This is the TI 34 calculator. I'm very similar to TI 30, not much difference at all. Here's my open parenthesis. Here's my open parenthesis key right here, and here's my closed parenthesis key right here. Okay, for every open parenthesis you type, eventually you're going to have a close. You're going to have to close it off the closed parenthesis. So you always have to have a balance between your parentheses here. All right. Okay, so how would we type this in here? I'm going to try to do that. So I would have an open parenthesis here. I would type in 10 times open parenthesis 113,865. Okay. Closed parenthesis. And then I'll say minus 572 times open parenthesis 1750. Closed parenthesis. And then we have to have a closed parenthesis to close out the entire numerator. Do we understand how I just typed in the numerator here? Like I'm just a numerator. You see that? That's the entire numerator. Notice the parentheses that I'm using here. All right, for every open parenthesis, you eventually have to have a closed parenthesis. This is the open parenthesis, which will be closed at the very end. This is an open parenthesis just to contain this 113,865. So I must therefore close it off immediately right here. Minus 572 times my open parenthesis just to enclose this number, 1,750. And then I close it off, and then I have an overall closed parenthesis, which closes off the initial open parenthesis I put to begin to type my numerator. Now I say divided by. Now we have to enter in our denominator, and we got to go get our square root function. Where is the square root function on your calculator? Well, on this TI-34, it's right here on a button, the square root. Your square root function may be above the button. It might be above your x squared button. If that's the case, you're going to have to hit your second key first then followed by your x squared button to access the function above the button. Okay. Where would it be on the TI-30 here? This is the TI-30. So on the TI-30, it's above my x squared button here. It's right here above my x squared button. So I would have to hit my second key first and then my x squared button to bring up my square root function. And the reason why I can't use this calculator is because it's dead. Okay, I got to get batteries for it, or else I would use this. This is the TI-30XS, the one that they recommend. But in all honesty, I mean, any other scientific calculator that affords you parentheses can take care of business. Now, can you use a calculator on the computer system to do this? I strongly recommend you do not do that, because a calculator on the computer system may not show you everything that you've typed in. Okay. You want to be able to see everything you typed in so you get a bird's eye view as to where you're going with this entire formula here. All right. So I would recommend that you have a calculator that shows you, what it is you have already typed in here, so you can see what's going on here. All right, divided by. Now I'm going to go get my square root. So I'm just going to hit my button, my square root button here. And there's my square root. Now I have to enter in my expression underneath the square root. Well, underneath the square root, I have the product of two things inside parentheses, or they're using brackets. Brackets, parentheses are the same thing. Okay. So I'm going to open up with a set of parentheses, type in all that stuff, and then close it off. Then times another bracket or parenthesis, everything that's inside there, another closed parenthesis, right? You got to make sure you keep it all underneath the square root. All right, so I'm underneath my square root, and now I'm going to type in what I see. Open parenthesis. Now I type in 10 times 37,802. You could have enclosed the 37,802 inside parentheses, not necessary. Subtract 572 squared, 572. And how do we square something on the calculator? There's two ways. You could just hit your X squared button right here, X squared. Or, ladies and gentlemen, you can hit your general power button, which is right here. This is your X squared button. This is how you raise something to a general power. I'm going to hit my general power button, and notice my cursor becomes an exponent, and I'll type in 2. You got to bring your cursor back down to level by hitting your right arrow key to drop it back down to level. And now I'm going to have a closed parenthesis times open parenthesis now 10 times 372,814. Subtract 1750 squared. Okay. And then a closed parenthesis. And then you can hit your right arrow key to get out from underneath that square root. Now we're no longer underneath the square root. Ladies and gentlemen, we've typed our entire expression in, and I would just kind of like scroll back through it to make sure that, you know, everything looks like it's been typed in properly here. Okay. So we typed in the entire expression. I mean the entire expression. Now, if you hit enter, you should get the 0.748. Okay, 0.748. Now, if you missed that, I'm going to show you the keystrokes again that you would want to go through. So first you want to hit your open parenthesis. Then you would type in 10 times 113,865. Subtract 572 times 1750. Closed parenthesis. Divided by. Now we got to type in our numerator. So now you got to go down, you got to get the square root. Get your square root. You got to get your square root. And then we're going to start by typing in an open parenthesis. 10 times 37,802. Subtract 572 raised to the second power. Hit your right arrow key to bring your cursor back down to level. Closed parenthesis. Times open parenthesis. 10 times 372,814. Minus 1750 raised to the second power. And then a closed parenthesis. You can hit your right arrow key to exit out from underneath the square root and then just hit enter. There you go. There's all the keystrokes to entering in. Those are all the keystrokes, literally, keystroke per keystroke. I left nothing out. And that will literally enable you to compute the correlation coefficient R. Did anybody get the 0.748?
I did.
All right, that's good to hear. Are we getting this out there, ladies and gentlemen? Anybody hung up? Are we getting the 0.748 for the correlation coefficient for this ordered paired data set? Notice, just as we suspected, this is close to +1, but it's not exactly +1, which indicates we still, and it is positive though. So this indicates, yes, we do have a direct correlation between the number of hospital beds and the number of employees in the hospital, but it's not a perfect direct correlation, okay? It's not a perfectly strong direct correlation, but it is a direct correlation nonetheless, and it's fairly strong. It is fairly strong. This is pretty close to 1. Pretty close. All right. All right. Any questions about that there? How to compute the Pearson correlation coefficient R for an ordered paired data set? And there you go. And this is just emphasizing something I already indicated there, okay? All right. Now, this is interesting. Statisticians have traditionally agreed that when we conclude that two data sets have a relationship, we can be satisfied with that conclusion if there is either a 95% or 99% chance that we're correct. This corresponds to 5% or 1% chance of being wrong. These percentages are called significant levels. You would get into significant levels and their importance lays on more so in a course in statistics when you start building what are called interval estimates or confidence intervals, and you start conducting what is called hypothesis testing for a population parameter value. All right, that you will encounter in Math 150, probability and statistics here at Mod. That's an elementary course in statistics, by the way. Okay. All right, so what's going on here? Significance levels, sample size. You're not really going to have to worry too much about that. Like I said, we're not going to get really too much into the significance idea of things. This is just saying if the absolute value of our correlation coefficient is greater than or equal to the value given in the table for either the 5% or 1% significant level, then we can reasonably conclude that the two data sets are linear related. For instance, what was our sample size? It was what, 10, correct? It was 10 there. We had 10 ordered pairs. And what was our correlation coefficient that we computed? I believe it was 748, I believe, correct? So you can see that 0.748 is pretty darn close to this 0.765, and this it's greater than 0.632 in lights and is less than 0.765. So generally speaking, we can say that, yeah, there is a significant linear relationship between the number of hospital beds and the number of physicians or employees in general. Okay. All right. But I'm not really going to emphasize that. I just hope we can compute the correlation coefficient R. All right, now, ladies and gentlemen, that we've computed the correlation coefficient R for an ordered per data set, let's turn our attention to the last aspect of today's lecture, which is trying to fit a line to our ordered paired data. In that process of fitting a line that fits our ordered paired data the best is called regression analysis, linear regression analysis, okay? Such big words, correct? But it is a very powerful technique to model your data, your ordered paired data, according to a linear equation, of which then you can use it to make forecasts or predictions. And this best fit line that we're going to show you how to come up with fits the ordered pair the best in the sense that it minimizes something called the sum of the squared differences that exist between the actual y values and the predicted y values squared. And this best fit line is guaranteed to fit your ordered pair data the best. There is no other line that fits your ordered pair data better than the one we can come up with called a regression line or the best fit line. And guaranteeing that is a branch of mathematics called differential calculus, because that's where the formulas come from that we're going to use to compute our linear regression or best fit line. Okay. So, ladies and gentlemen, we seek a linear equation of the form of y equals mx plus b, where m is the slope of the line we learned, and b is the y-intercept of the line. Of course, the line will go through the y-axis at that number b, and the slope of the line is a measure of the rise over run we experience as we navigate from one point on the line to some other point. Now, in statistics, they got these letters all different and turned around a little bit. They have y is equal to a plus bx. But ladies and gentlemen, there is no difference here. What they call b is what we call m, the slope of the line. These are the same. And what they call a is what we call b, the y-intercept. So for this equation here with this notation, a is the y-intercept, lowercase b is the slope of the line. Up here, m is the slope of the line, the lowercase b is the y-intercept. It's just a matter of notation, okay? So just be careful as to what is what here, and how you know to tell which is a slope versus which is the y-intercept. All right. Okay. Okay, now, how do we find, you know, this A and this B for the purposes of developing this linear regression equation here? A is the y-intercept. For the purposes of this, how they have it labeled in this equation, that's the y-intercept. B is the slope of your line. So how do we compute A and B using our ordered pair data set? Well, like I said, from differential calculus, they did come up with these marvelous formulas, which enable us to compute those values. Furthermore, I want to draw your attention to the fact that we're going to have to find the slope of our linear regression equation, linear regression line first before we compute the y-intercept, because notice this number b is needed to compute the y-intercept A. That's why you need to compute b first before you can compute A. But there they are, ladies and gentlemen. I want you to jot those formulas down. Again, these formulas are geared to give us our linear regression equation, which is of the form of y equals a plus bx. B is the slope, A is the y-intercept. Please write these formulas down. Just jot them down now, if you can do that. Notice we got a bunch of summation notation again from our ordered pair data set. All right, so go ahead and write those down. And I will probably take a picture of them on my phone too, because I'll have them handy. All right. Yeah, you don't have to memorize these formulas, ladies and gentlemen, but you need to have them handy. When you go to do Alex homework, quiz, or exam, make sure you have these formulas handy. And you can also have an example right next to them, so that it will help you to maybe do a problem or two on Alex, okay? That has you computing the correlation coefficient R, and also now computing the linear regression equation that best fits your ordered pair data. Let me know when we're all good on that. I guess I'll take one student's word for the rest of us, but get them written down.
I'm good.
All right, anybody else still need more time jotting these down, or? Okay, so yeah, just make sure you have those in a conspicuous place whereby you can access them when it becomes necessary. Let's see if we can use these formulas now, ladies and gentlemen, to actually find the linear regression equation for an ordered paired data set. And I would suspect we're probably going to find it for the hospital data set we collected. Yeah, they're using the same data for the hospital ordered pair data that we collected way back. Notice the summation values are dropping in where they belong. And where did we compute all these sums? Do you remember where we computed them? We computed them, ladies and gentlemen, way back here for the purposes of finding what? The correlation coefficient R. Do you agree? We've already computed all these. So this table is nice because not only is it going to enable you all the information to compute R, the correlation coefficient, but it's also going to enable you to compute the linear regression equation. Okay. So that's why that table is nice to have. So they drop everything in where it belongs into this formula to compute the slope of the linear regression equation, which turns out to be 2.708. Just make sure you can do this on your calculator. Again, I strongly recommend if you want to type this in all on one line, you need to enclose your entire numerator and your entire denominator inside parentheses. If you don't do that, you're going to get a logical error because these parentheses force precedence, correct? By placing all this in the numerator inside parentheses, your calculator is going to take care of the multiplication here and here first, and then the subtraction. And then it'll take care of the multiplication here and the exponent here, and then the subtraction. And then it will do what in between? Then it'll divide the numerator result by the denominator result. If you don't have these quantities inside parentheses, that's going to cause a big problem. If you don't have these enclosed inside parentheses, here's what your calculator is going to do. It only obeys the order of operations because that's how it's been programmed. So your calculator, what it's going to do, ladies and gentlemen, is it's going to multiply this together here and this together here. But then it's going to take only the product of this and divide it by the product of only this. That's going to give you a logical error. Because we don't want just this divided by just this. No. No, we want the whole numerator result divided by the whole denominator result. These parentheses are critical, or else you will not get the correct result. So make sure you always enclose your entire numerator inside parentheses and your entire denominator inside parentheses. Very important. All right, get on your calculator, ladies and gentlemen. See if you can dial it up. Do we get about 2.708? Let me know if anybody's getting that out there. Are you able to get that slope of that regression line as being about 2.708? Let me know if anybody's getting that out there. Did somebody get it?
Yes, I did.
Okay. And I'll show you, I'll show you all the keystrokes you got to go through here. If you're still struggling with that, this would be the verbatim keystrokes you literally do on your calculator. Open parenthesis, 10 times the 113,865, subtract 572 times the 1,750, closed parenthesis, that's your entire numerator, divided by now your entire denominator. Open parenthesis, here's your entire denominator, 10 times 37,802, subtract 572, raised to the second power, bring your cursor back down to level. You might have to hit your right arrow key to do that. And then a closed parenthesis to close off your entire denominator. And then just hit your enter button and you should get it. Okay, enter or equal button. And you should get about 2.708. Are we getting that?
Yes.
Okay. So yeah, I mean, whether or not you insert parentheses in a complicated calculation will make or break you. If you don't do it correctly, you're not going to get the correct answer. Your calculator is only going to do what it was told to do. It's a very stupid machine. You have to tell it exactly what you want it to do. And if you don't enclose a numerator and denominator side parentheses, it's only going to abide by how it was programmed. and it was programmed to obey the order of operations strictly. Okay, so you have to force it to take care of the computation in the numerator first and the computation in the denominator first before it actually divides the two. Very important. Okay, so that's the slope of our linear regression equation, 2.708. Great. Now, ladies and gentlemen, we're going to use that value of B to compute our y-intercept of our linear regression equation. And this is the formula for it. And notice that our value of B, which was the slope we just computed, was 2.708, is needed for this formula. That's why you compute the slope first before you compute the y-intercept. Get on your calculator and dial this up. Make sure you enclose your entire numerator inside parentheses here. Now, you don't have to enclose the 10 in the denominator inside parentheses because it's just a single number. But if you ever have the sum or difference of terms, you always enclose it inside parentheses for the numerator and denominator of a fraction. All right, dial it up. Do you get about 20.102 for the y-intercept? All right. And when you do that, hopefully you get that, you will have the linear regression equation. This equation fits that ordered paired data set the best. You cannot do better in fitting that ordered paired data set with any other line than this one right here. This is called the optimal line. It doesn't get any better than this. And that's guaranteed by a very powerful branch of mathematics called differential calculus. Okay, so we got a very powerful branch of mathematics going to bat for us in us saying such a thing. Okay. And the derivation of these equations we've been using to find the slope and the y-intercept for the linear regression equation, that derivation is beyond the scope of this course. If you absolutely want to see it, well, you would have to know a little bit of differential calculus, ladies and gentlemen. I'll be honest with you. You have to. So it's beyond the scope of this course. But these equations we've been using have a name. They're called the normal equations. So the equation for finding B and the equation for finding A of our linear regression equation, these are called normal equations. That's their name. They're called the normal equations, okay? All right. You don't really need to know that. I'm just throwing it out a little extra for your money there, okay? Called normal equations. All right, let's move on. Now, why go through all that? Well, there's a reason. Because, ladies and gentlemen, what they did, remember the scatter plot we made for the hospital data? They then graphed this linear equation, overlaying it on the scatter plot. They graphed this linear regression or best fit linear equation, and there it is. There's its graph, and you can see that in general, it fits most of the data points very well. It fits these data points very well. There's a very good fit here. This point almost literally lies right on the line. Here's another very good fit. This is not a good fit. Okay, that's the reason why our correlation coefficient is not perfectly 1, because this data point is quite a distance away from our linear regression equation here. All right, so some data points are very close to our line, and some are a little bit what? Further away. Do you agree? Some are a little bit further away. But in general, you could not fit any other line than this line and fit this ordered paired data any better than what this line is doing here. If you try to fit a line like this would be a lousy fit. Does a very good job for this data point here, but it has no justice for the rest of your data points out here. Okay, suppose you put a line like this through your data. Well, it does a pretty good job in fitting these data points quite well, but it does a very lousy job as far as these are concerned. These are very far away from that line. Trust you me when I say this line is the best fit line for this ordered pair data set. It's the best fit line. It minimizes something called the sum of the squared differences between the actual y values, like the actual y coordinate of this point, and the predicted y coordinate according to our linear regression equation. It minimizes the sum of these squared differences. All right. So it is the best fit line. Okay, now That's great. That's beautiful. But Liz, oh, another thing is notice the slope of this line is positive, and that's why we have a direct correlation or a positive correlation between the number of hospital beds and the number of employees. That's a rising line, positive slope. We can now use this linear equation to make predictions. Okay, that's the point of regression analysis, is to model your data according to an equation that can then be used for predictive purposes. All right. For instance, let me show you what I'm talking about here. Suppose I wanted to predict how many employees a hospital would have, Les Amin, if let's say that the hospital has, let's say 75 beds in it. 75 beds in it. Well, guess what? We can use our equation to make a prediction. All I got to do is take 75 and substitute it in for what? The X variable here. Get on your calculator and dial this up. What's 20.102 plus 2.708 times 75? Tell me how many employees such a hospital would probably be predicted to have if it has 75 hospital beds. So do this on your calculator. 20.102 plus 2.708 times 75. Tell me, how many employees would we predict that hospital to have? You do it on your calculator, and I'm gonna get an approximation from my graph here. I would say just over about 200. Is anybody getting somewhere like maybe 225 or something? I don't know, 210 or something, or
223.
23.
23. You can see it from the graph, can't you? If you got 75 hospital beds right here, you project it up, you hit the least squares regression line, project it horizontally back to the y-axis and read off that value. Yeah, it looks like about 223, right about there. It's a little bit larger than 200. Yeah. So I have a question for you. If a hospital, Les Amin, has about 45 hospital beds in it, from the graph, what would be your estimated number of employees for such a hospital? Well, go to 45, project it up to hit the graph, and then project it horizontally. A ruler would be nice. Horizontally back to the y-axis. And what does it strike about? About how many employees for a hospital with 45 beds in it? About what? Well, maybe
140.
yeah, 140, somewhere in there, give or take a couple, correct? About 140 employees. You see that there? So we can use this line for predictive purposes. Now, here's a very good question. Would we have any faith in making a prediction for a hospital that had 300 hospital beds in it? Anybody want to weigh in on this? Would we have any faith in predicting the number of employees for a hospital that has 300 beds in it? Why or why not? This is a pretty deep question, so don't feel bad if you don't know the answer. I'm just wondering if anybody's got any input for what I just said there or asked. Would you have any faith in making a prediction of the number of employees for a hospital that has 300 hospital beds in it? Why or why not?
The number that I got, once I put that in the equation, it's way bigger than what the graph goes up to. So I don't think it would work then for this
So we
graph.
probably would not have much faith in that, okay?
Yeah.
You're right, and you're onto something really important here, ladies and gentlemen. When you use, this is very important, when you use a linear regression equation to make predictions, you got to make sure that you're only predicting values for Y. For values for X that are within the range of the values of X of the ordered pair data you collected. What was the range of the X values or the X coordinates for the data we collected? What was that range? Oh, I forgot. What was it about, well, the X coordinate data? Let's see. I completely forgot it. We'd have to go all the way back. X ranged from about 28 to 95. Do you agree? So, ladies and gentlemen, if you're trying to make a prediction for Y for some value way beyond the range of the X values of the ordered pair you collected, you would not want to put much faith in such a prediction. Here's why. The reason why is because we know that we have a linear relationship between X and Y for X values that range between about 28 to 95. But can we say that with certainty for values of X outside of that range? Does the relationship necessarily remain linear? Do we know that for sure? We don't know that for sure. As soon as we go beyond an X value of 100, ladies and gentlemen, who knows what happens to this relationship? Maybe all of a sudden it becomes what? Suddenly nonlinear in some sense. Maybe it becomes suddenly nonlinear. We don't know that. We don't know if it remains linear or becomes drastically nonlinear beyond that value. For that reason, be careful when you use a regression equation to make predictions. You only want to make predictions for the values of X, okay, that was the values of X that you collected in your ordered paired data. So you only want to make predictions for X that for values of X that are between 100 and what? What was it, 25 or 28? I think it was 28. Okay. So we would have faith in predictions for Y if we make a prediction for X lying in between these values. Because this was the range of the X coordinates of the ordered paired data that we use to build this linear regression equation. So you never want to extrapolate outside of the range of X to make a prediction for Y. That's a dangerous thing to do. Okay. This is just re-emphasizing the relationship between the correlation coefficient and the signature of the scatter plot of the ordered pair data. Notice, ladies and gentlemen, if all your ordered pairs or points you collect in the field lie perfectly on a line, then your correlation coefficient would be perfectly equal to 1, as this is a what? Perfect direct correlation between X and Y for this diagram over here to the right. Or if all your ordered pair data points lie on a falling line perfectly, then we would expect R to be not positive 1, but to be exactly what? Negative 1. In which case you'd have a perfect negative or a perfect inverse correlation between X and Y. Here's a fairly strong direct or positive correlation between X and Y. We would suspect R to be very close to positive 1. And notice it's pretty darn close, 0.90. Notice these points are a little bit scattered further away from the line of best fit. And because of that, we would not expect R to be, really close to positive 1, although we still have a direct correlation between X and Y. We would expect R to be less between 0 and 1 somewhere, okay, like this, maybe 0.50. All right, so do we understand the relationship between the value of R and the strength of relationship we can ascertain from the scatter plot? Okay. And this is just showing you what I've been arguing here. These are all negative or inverse correlations between X and Y. The one furthest, the diagram to the right, here is a perfect -1 for R, as all the points lie directly on a line. The middle scatter plot indicates a less strong inverse correlation between X and Y, but nonetheless pretty darn strong, -0.9. And the diagram to the left here represents, it's an inverse correlation between X and Y, but it's not nearly as strong as the other ones. So it'd be, R would be about -0.50. That's about right. Okay. All right. And here they're having us use the regression equation we found for the hospital ordered pair data set to make a prediction. If a hospital has 65 beds in it, we would literally replace the X variable in our linear equation with 65, multiply it by 2.7077 and add to that 20.120 to predict that we would, such a hospital would have about 196 employees. Okay. Would you have faith in this prediction? Yep.
Yes.
Because 65 lies between 28 and 100. Do you agree? It lies within the range of the X coordinates of the ordered pair that we collected. So yeah, I'd have a fair amount of faith in that prediction, sure. All right. All right, now, some people think that just because there's a strong correlation between X and Y, they think then, okay, well, the X variable must cause the Y variable to do what it does. In other words, ladies and gentlemen, do you think that correlation necessarily implies causation and vice versa? Do you think that's always true? The answer is no. Just because two variables, X and Y, are strongly correlated does not mean that they are basically cause and effect for each other. Very important. It could just be coincidental that X and Y are correlated with each other. That in reality have nothing to do with each other. All right. Let me give you an example. Here's a perfect example to illustrate that correlation does not necessarily imply causation. All right, suppose, ladies and gentlemen, I define my X variable to be equal to the number of air conditioners that are turned on in the city during the summer. Number of air conditioners turned on, okay? And suppose that I define variable Y to be the number of crimes that are committed within that city during the summer. Number of crimes. Okay, now, check this out. Data has shown that when temperatures rise and when the weather is nice, in general, crime tends to rise. Data has confirmed that. I'm not saying that from my opinion. I've actually read studies where the numbers actually show that. Okay. So, ladies and gentlemen, and when the temperature rises in the summertime, we are more prone to what? If it gets too hot and humid, we turn on the air conditioner. Although there's a strong correlation between air conditioner use and the number of crimes in a city, does that imply then that if I flip on my air conditioner, that's going to cause somebody to rip off a gas station? Is that true, ladies and gentlemen?
No.
No. And that's a golden example to illustrate where you can have a strong correlation between X and Y. And yet there's no causation between X and Y. Just, yeah, when it's hot and humid, generally speaking, yeah, people start firing up the air conditioners. And the crime rate tends to increase. But don't think for a moment, just because those two variables are correlated, because they are directly correlated, don't think for a moment that, air conditioner use is any, cause for increased crime rates. There's no causation here. There's correlation, strong correlation, but there's no causation. So you got to be careful. Normally, now listen, normally correlation is related to causation. Normally, for most variables X and Y in the real world. But not always. So be careful of that. Don't think that, strong correlation always implies causation. Normally it does. But that's not always true for all variables X and Y, or for all data. All right. So be on guard for that one. That's a common mistake, to think correlation always implies causation. All right, we're done with this, ladies. I want to see if we can go to our textbook and have a little bit of fun. If technology allows us to do so. Let's see, where are we here? Wrong. Now, I think I opened up the book. Oh, here it is. Okay, yeah, let's go to our textbook. This is section 11.8. And we're working with correlation and linear regression. So let's see. 11.8 is way down here. It's in the chapter that's entitled Statistics. We're going to go to 11.8. Correlation and regression analysis. All right, let's see if we can maybe do a problem or two out of the practice problems here. Oh, by the way, please do take the time to look over the examples that are laid out in this section. It's only going to help strengthen, ladies and gentlemen, your understanding of what it is we just went through here during class, okay? Oh, there's the formulas again. If you lose them, they're on the PowerPoint, but if you lose them, they're in your textbook, section 11.8. They actually walk through examples here. Look at that. They walk through an example. So it's all here. It's all either on the PowerPoint or in your textbook. So please take the time to, just kind of maybe look through some of that there. That'll help out. All right, let's see if we can do a problem here. All right, here's what I want you to do. First of all, ladies and gentlemen, we're going to do this in pieces. We're going to do this in parts. This is all going to be a part of classwork number 1, okay? Number 1, or the first part of classwork 1, I want you to draw a scatter plot for this ordered pair data. Now, graphing paper would be nice if you have some, but if you don't, don't worry about it. You can, just do the best you can with a ruler and paper and just lay off a scale on your x-axis and a scale on your y-axis and just plot these points to the best of your ability. You don't necessarily have to have graphing paper, but I want us to draw a scatter plot first. Let's do that first, and then we'll move on, okay? Go ahead and make a scatter plot for that ordered pair data number 11 here. Okay, so the scatter plot would look like this. Between X and Y here. And did anybody get this scatter plot here that looks like this? Notice the X axis, they label it from 0 to, looks like 7. That's well within to accommodate the range of data, the X coordinates of the ordered period data. The Y axis, they laid it off from 0 to 28, spaced a tick mark 4 units apart. That would accommodate the range of the Y coordinate values of our ordered pair data. Did anybody get that scatter plot? Does that look like about right or not? And again, graphing paper really should, I mean, that would be the nice paper to use for, accuracy purposes. But, I mean, with a ruler, you could still be somewhat fairly neat and duplicating this scatter plot. Okay. But ladies and gentlemen, you can see clearly that from the scatter plot, do we have a positive or a negative correlation between X and Y? What would be the case? What's that? Negative?
No, it's positive, ain't it?
That is positive. Yeah, this is a rising line, which has a positive slope. So this is a positive correlation between X and Y, or we say a direct correlation between X and Y. Would you suspect that the correlation coefficient R is going to be then very close to 1 or not so close to 1? I mean, is it a strong direct correlation between X and Y? Does it appear that all these points lie on a line or very close to a line?
Yeah.
Looks pretty strong, doesn't it? Yeah, we would suspect a correlation coefficient for this ordered pair data set to be pretty darn close to 1. All right, we're going to convince ourselves because we're going to do that next. All right, so the next thing I want to do here, ladies and gentlemen, that's the first part of classwork 1. I want you now using the formula to compute the correlation coefficient R for this data set. So go ahead and compute the correlation coefficient R for this ordered pair data set. So do that now. Make sure you make the table, with the X column, the Y column, the X squared column, the Y squared column, the XY column, just like it was on the PowerPoint, because you're going to need those sums to fit them into the correlation coefficient formula R. Okay. So, let's go ahead and, see if we can, maybe do that. What I might be able to do here is use my snipping tool here. I'm going to try something here. And I'm going to snip this ordered pair data set here. There we go. And then I'm going to bring back the PowerPoint presentation, ladies. I'm going to go back to that correlation coefficient formula R. Where was that thing here? Yeah, right here. Okay. And then I'm going to bring this up. Whoops. And I don't know, can I fit it somewhere? Maybe like right here. All right, does that help you? I'm going to leave that up there, ladies and gentlemen. There's the formula for R. You just have to make a table to find all these sums and then substitute them in where they belong. Go ahead and do that. We'll call this part of classwork number 1, second part of classwork 1. All right. So, here is my data table that I made to help me compute the sums of the respective columns. Then I fed everything into the correlation coefficient formula and went through and computed about 0.977. Did anybody get 0.977 for the correlation coefficient R?
I think it's gonna take some practice.
All right. You see what needs to go into it though, correct? All the stuff we need here. That table is important because it helps you to compute all the summations you need. And
I
it's-
got most of the table right. I just didn't finish it yet.
Okay, all right. All right. Go ahead and finish that up and see if you can get that 0.977, which confirms our suspicions. That looks like a very strong direct correlation between X and Y, as those points indicate that we do have that because they're very close to lying on a line, all of them. They're not scattered too far apart from each other, so it makes sense that this would be a very strong direct or positive correlation between X and Y. That's why R is very close to 1. And ladies and gentlemen, while we're at it, then we can then use this data and all that we've computed to find the regression equation. So that would be the next thing I want you to do with this classwork is find the least squares regression equation, where it's of the form of y is equal to a plus bx. Do you remember that? Where we got to find the slope first. And what was that equation? What was the formula? Okay, here it is. It's n times sum of xy minus the sum of x times the sum of y. And this is all divided by n times the sum of the squared x values minus the square of the sum of x. Make sure you enclose this all inside parentheses. That'll give you b. And then once you find b, you can then find the y-intercept of the linear regression equation by using this formula here. It's the sum of the y values minus b times the sum of the x values divided by n, where n is the number of ordered pairs you have in your data set. Okay. All right, so go ahead and see if you can find the linear regression equation. Since we got everything laid out here in our table, it should not be a difficult thing to do. We've already done all the heavy lifting in computing all these summations. Now it's just a matter of plugging things in. All right, go ahead and do that. And we'll wrap up this this classwork here. And there you go. That's the rest of the computations. I showed you how to find the linear regression equation using the normal equations. So once you build your table and find all your summations, then, like I said, all the tedious work is really behind you per se. It's just a matter of plugging things into the respective formulas to find R and to find the slope and the y-intercept of the linear regression equation here. So this would be the line of best fit right here. This is its equation. That is the line of best fit there. And if you were to overlay the graph of the linear regression equation onto your scatter plot, it would look like this. And you can see that there's a very good fit between that line and pretty much all the data points in that data set. And that's why the correlation coefficient is very close to +1. No surprise there. All right, this is, by the way, the TI-84 calculator, a graphing calculator that can do regression and scatter plots directly. But you don't need a calculator like this, ladies and gentlemen. I'll just have you do some of these small data sets manually. It's no big deal. You don't have to have a graphing calculator like that. But is anybody getting these results here, or is I mean, anybody confirm any of this? Anybody at all?
Yeah, no, this whole session has just been it's gone over my head.
It's pretty tedious, you gotta admit, but that's why you want to watch the video, and try to take it in a second time. I think that'll help a lot, all right? But you can see the calculations are just tedious, time consuming. It's time consuming to make this table, sum everything up, and to put things into where they belong into the formulas we're using, okay? All right, but with practice, ladies and gentlemen, this will come into focus. You just have to maybe watch the video again and just practice a couple of these problems, Try a couple of them out in your textbook, some odd problems, make sure you can check your answers, all right? So do some odd problems. The answers to the odd problems are in the back of your textbook for a little extra practice there. And I'll give you some practice on Alex, finding R and computing a linear regression equation. All right, so we're all out of time. And